This is supposed to be a winter school, so the idea is to get some information across. I have a lot of slides, and I have a good story to tell you. But seriously, I do not mind being interrupted. I welcome questions. And if you ask them, I will, of course, try to answer. I'm going to talk about nanomaterials, but in a particular context. I'm going to talk about nanomaterials that are formed by spontaneous phase separation. So phase separation is very common. We all know examples of phase separation. You put oil in water, they separate. And there are many, many, many examples. But if you have two different semiconductors, and they spontaneously phase separate on a nanoscale length scale, then you have a heterojunction at the interface. Heterojunction between, in the classic sense of semiconductor physics, heterojunction between material 1 and material 2. And that's what I'm going to show you is the heart of this. Okay? We're talking about two different organic materials that I put into solution and cast a film. The solvent evaporates. And as the solvent evaporates, the two components phase separate. It's not just an accident that they phase separate. Basically, polymers always want to phase separate because there's no entropy of mixing. You know, if you put sodium chloride into water, you might ask even, why is it soluble? Because sodium chloride is a very strong ionic solid. And the answer, as you all know, is that when you put sodium chloride into water, the entropy really plays a big role. There's so many places, so many different ways that you can distribute the ions that the entropy of mixing is very large. But when you have a high molecular weight polymer, this was shown, many years ago by the famous chemist Paul Flory, the entropy of mixing goes away because if you pull on a polymer, long chain polymer, the whole chain will move. So as the polymerization index gets large, the entropy of mixing goes to zero. So these things are always going to phase separate. And that's what I want to tell you about, but I want to tell you about it in the context of these images. These are two images. I'll show you a number, but these are solar cells, plastic solar cells. You can see the size of them by comparing. These are on being tested for lifetime on a rooftop in a small town, actually near Boston, on the northeast part of the United States. This is another image, and you have to look at it fairly closely to see what I'm trying to show you. This is being taken through a window, okay? And you see that you can see the cars here, okay? So this isn't a product, but it's a concept that really will be a product. Transparent solar cells, semi-transparent solar cells, right? There are huge windows on all big cities, buildings, right? Tel Aviv, Shanghai, New York, whatever. All those buildings have an incredible area of window space. People inside don't want the sun to shine right on them, so they put an absorbing layer on those windows. So the goal here is to, like a pair of sunglasses, about that optical density. The goal here is to replace that with solar cells. that will be semi-transparent, produce electricity at the same time. So this gives you some idea of where this is. All right, we want to convert sunlight to electricity. Three-step process. Obviously, the first step is to absorb the photons. That's basically a problem that was solved in 19th century chemistry. German dye chemists, for example, made highly absorbing dyes that have long lifetimes. Well, it's evolved since then, but that's when that began, out of organic materials. And we're using, that history, we're putting those kinds of dyes into these semiconducting polymers. And they have quite high absorption coefficients. So I can absorb light. It's important, of course, that I absorb sunlight if I want to make solar cells. So one needs to optimize the absorption spectrum with respect to the solar spectrum, and I'll come back to that. Now the second step is that I need to separate charge. Not sufficient just to absorb the photons. I need to have a charge separation process, make electrons and holes, which I then somehow have to collect at the electrodes. So those are the three steps. That's what you do in silicon solar cells. That's what you do in inorganic solar cells. And we have to do the same thing here. And of course, we want to, as I said, we want to try to get as much of the solar spectrum as we can. And we would like to prevent recombination of those photo-generated carriers before they get out, so that I can get relatively high efficiency. In 1992, we made a discovery in our labs. At the time, I had a postdoc, Serdar Serçivci, who is a professor in Austria now. And the discovery was that when a photon comes in and is absorbed by a semiconducting polymer, this is just one example of polyparaphenylene, vinylene with side chains. But the statement is very general. When a photon comes in and is absorbed in this semiconducting polymer, promoting an electron from the valence band to the conduction band or the pi band to the pi star band, if there is a fullerene nearby, one gets photoinduced electron transfer. Okay? I'll show you that photoelectron transfer process is very fast, and as a result, it's very efficient. So almost 100% of the photons lead to electron hole pairs. Now, the next question is how do I get them out? Okay? The absorption, you understand. I was going to say it's a solved problem. In principle, yes, but I need to generate materials that will give me efficient absorption of the solar spectrum. The ultra-fast charge separation separates charge very effectively. I have to get them out. And the problem with getting these charges out is that I am insisting on making a low-cost technology. So I want to do everything by casting the materials from solution. So what I'm talking about in these films is highly disordered, non-crystalline material, highly disordered. The recombination length is less than 100 angstroms, maybe 100 angstroms. The length over which an exciton can diffuse before a recombination, less than 100 angstroms. This is not single crystal silicon. So even with a thin film, the thickness of this film is probably 100 to 200 angstroms. Even with a thin film, you can't get them out. So the solution, the idea, was to create a material like this is of course a cartoon, where the black is the fullerene and the white material is the polymer, and both of them are, it's a bicontinuous network. Each of the networks is percolated, fully percolated, so that when an electron is transferred from the polymer to the fullerene, it can find its way along that black path to the electrode, and similarly with the other. I have to do that, and it has to be this length scale of the phase separation must be on the nanoscale, something like 10 to 20 nanometers. 20 nanometers ideal. Otherwise, I'll lose the carriers before they get to the phase separating interface. So that's why I call this self-assembly of a bulk heterojunction material by spontaneous phase separation. What do I mean by a bulk heterojunction? What I said before is that when you have an interface between two semiconductors, you have a heterojunction. Okay? But the interesting thing about this idea is that there's not one heterojunction. There's heterojunctions everywhere inside the bulk of the material. And at every one of those heterojunctions, one can get, and one does get, photoinduced charge transfer. Want to see it? So here it goes. Photon came in. That was great. Let's do it again. Okay, photon's going to come in. I'm going to promote an electron. I'm going to promote an electron from here to here, and the electron is going to transfer here. Why? Well, obviously because there's a state here which is not filled, and it's at lower energy, so that it is energetically favorable for that electron to transfer. Okay. Now, that happens in 50 femtoseconds. That's 2 orders of magnitude faster than the first step in photosynthesis. Quite interesting. Very efficient process. Photosynthesis has been evolving for a long time. One of the reasons that it's so fast is that this is not right. I mean, there's basically a continuum of states here. I'm talking about a very high molecular, relatively high molecular weight polymer. So the energy levels quantization, I mean, there's basically a continuum of states. Similarly here. So when the electron transfers, gains energy, but fundamental rule is you have to conserve energy. So you should ask, well, where did that energy go? And that's often in charge transfer problems. That's often a bottleneck. In this case, it's not, because when the electron transfers, the hole can kick to a higher energy, Coulomb interaction. There's no need to wait for a fluctuation of a phonon, whatever. So it is really fast. 50 femtoseconds. It's been time resolved. Here is the highest resolution data. This was from Brabeck et al., 2001. So what they did was to look at the photoinduced absorption. You have a film. You hit it with a very fast laser pulse, something like 10 femtoseconds laser pulse. And then you watch what happens, okay? And in the pure film, without the fullerene, what happens when you hit the film with you absorb light, you make these photoexcitations that I was showing you here. And of course, those photoexcitations promoting an electron from a bonding to a non-bonding state, to an anti-bonding state, you would expect, and in fact, you do get changes in the bond length, okay? So after that pulse of light is absorbed, the molecule rings. It's just like taking a violin string and plucking it. It's going to ring. And in a violin string, that ringing is the harmonics of the string. But in a long chain molecule, that ringing is the amplitude modes of vibration that you see when you study Raman scattering. And there it is. You see, there's the photoinduced absorption is modulated by these ringing. You can see those peaks. If you look, first time you look at them, you say, well, maybe it's just noise, but it's not noise. If you Fourier transform that ringing, you get this spectrum, which I think is difficult to see. I apologize for that. But the Fourier transform of that ringing is the Raman spectrum of the polymer. So we know what this is coming from. This is just telling us that after exciting with a short pulse, polymer is just ringing, gradually dies out. But the you know, these are 10 to the minus 13 seconds or so, femtosecond time scale. Now you do the same experiment, but you put the fullerene in. Okay? And this charge transfer is fast, and it's also random in time. So now there's no longer any correlation, and all these oscillations get quenched, and you just see this decay. So you know immediately that the time scale is something like 50 femtoseconds. That's really fast. Now, how fast is it? What difference does it make? Well, the answer is that there's no competing reaction. Many of these materials, many of these polymers have some luminescence. And say a typical luminescence decay time, photoluminescence decay time, will be several hundred picoseconds, even close to a nanosecond, but say 100 picoseconds. In other words, 3 orders of magnitude slower than this charge transfer time. So the quantum efficiency for the charge transfer then approaches 100%. Because of this energy gain, this photoinduced transfer process is really fast. It's sufficiently fast that the probability of separating charge is essentially 1. For every photon that's absorbed, you get 1 separated electron in 1 hole. The electron is going to be on the fullerene network, and the hole is going to be on the polymer network that I showed you a moment ago. Yeah.
Just 2 questions.
Yes?
One technical question, how did you measure this graph in femtosecond resolution?
Say it louder.
How can you measure femtosecond resolution? How technically do you do this?
Well, I mean, the answer is you have to know how. I mean, and the first requirement is that you have to have a laser system that has a pulse width of, say, 10 femtoseconds. You can buy that, or you can build that. And then what you want to do is you want to have, you want to split the beam so that the exciting pulse comes into the film, and then you want to come a little bit later, 100 femtoseconds later, 50 femtoseconds later, with a probe beam. And the way you delay is you just put a mirror in, put a little extra distance, and the velocity of light takes care of that. So the time resolution is not an issue, not so difficult. You just have to delay one pulse with respect to the other by a millimeter or a centimeter or whatever the time is that you want. And that's not so difficult. Translation stage, it takes care of that. You need a good laser system. So that's a simple answer to a complex experimental question.
Just another question.
Yes?
What is the size of the heterojunction, the depletion region heterojunctions overlap when you place your network this close?
Let me see if I understand the question. You want to know whether these networks are really there? I'll show you. You want to know how fast they form when I cast the solution?
No, but when you describe a heterojunction,
Yes.
you add a characteristic length, means the size of the depletion region, whatever.
The characteristic size here, as I said before, is something like 20 nanometers. For the dimensions of a nano domain, and the thickness of the film is about 100 nanometers. I think this will be clear in a minute. If it isn't, ask me again. But I'm going to show you. I think we'll take care of that. So here, yeah, for example, here, that's just a cartoon. This is an electron microscope image, and here's the 100 nanometer bar. And what I'm doing is just electron beam coming down. I'll explain this in more detail later. But what I want you to see here is, of course, this structure in the image. If this is 100 nanometers, then you can kind of tell already that the characteristic size of these different domains is about 20 nanometers. Okay? And you also see, for example, here, I can follow a black network over long distances. The critical distance is, of course, the thickness of the film, which is only 100 nanometers. The black material here is the fullerene. The contrast comes from the fact that an electron beam going through this material interacts with the carbon nuclei, it's mostly carbon, in the material. There's the probability of direct Rutherford scattering, for example, direct head-on collision is very small. So mostly the electrons in the electron beam are small angle scattering. In effect, like a index of refraction in an optical phenomenon. So the electron beam goes a little bit more slowly through the fullerene because there's a higher density of carbon nuclei. A little bit faster through the polymer because it has a little bit lower density of carbon nuclei, and I get the contrast in that way. I'll come back to that. But here is an image of a real material which is bicontinuous, or seems to be, and has the right length scale. So that's a bulk heterojunction real material. And it was self-assembled by casting from solution. And every place where you see an interface, you have this heterojunction electronic structure which gives you charge separation. I'm just trying to show you a little bit here of what systems. So this is this is poly-3-hexylthiophene, which many people have used to make these solar cells. We can make solar cells with this and the fullerene, about 5%. Okay? If you take this system, it's a little bit more complicated molecular structure. Has a carbazole unit here and a kind of a donor accept. This is the repeat unit. And if you use that structure with a fullerene, you can get about 6.5%. This one has a smaller gap heading out toward the infrared, which is good, but for reasons that I'll tell you later, not quite as high efficiency. This is a very interesting polymer which has emerged recently, and people have reported 8% efficiency. So this is about new materials. The reason that this gives 6 and this gives 8 and this only gives 5 has to do with very fundamental physics of the semiconductor physics, and I'm going to try to explain that to you. But the picture I'm showing you here is a picture that is a design to show you something about the cell. Okay, so I need 2 electrodes. One of them has to be transparent, or I don't get any light in. So I'm using indium tin oxide. I'm using aluminum on the other side. I make this donor acceptor, this heterojunction, bulk heterojunction material using one of these 2 components for the donor and one for the acceptor. And then I use this conducting polymer to help with the injection, or rather the extraction of the charge. Now, when I've made this device, I made this material, at every one of these junctions, you get charge separation. So I have electrons. This is a schematic image of the cross section. Okay. Now, I have to tell the electrons to go up and the holes to go down, or vice versa. I have to break the symmetry. If I don't break the symmetry, even though I've got charge separation, nothing will happen. How do I break the symmetry? Well, that's actually pretty easy. I use 2 different electrodes with different work functions. If you think about it a moment, the electrons will always go to the lower work function contact, and the holes will go to the higher work function contact. So I can create this bulk heterojunction material by spontaneous phase separation, and then I break the symmetry by simply, and I don't mean to minimize it, but by simply using 2 different materials with different work functions. So this is real stuff. This is being made now in manufacturing plant. I'll say something more about that, by a company that is called Konarka, Konarka. This is a plot of the kind of data one expects to get, current versus voltage. In the dark, of course, this is a diode which has nearly 0 current and then turns on in forward bias. But when you shine light on, one gets photogeneration of carriers. One collects them at the electrode, and you get a short circuit current because of the built-in potential that comes about from that heterojunction. And then when you change the voltage, you compensate that internal voltage with an external voltage, and at some point the current goes to 0. We call that the open circuit voltage. The maximum power point is here, and that is like in any battery, when the external load is equal to the internal resistance, and the fill factor is this area over this area, and the efficiency is just the short circuit current times the open circuit voltage times this fill factor over the incident power. So I need to understand what limits the short circuit current, what limits the open circuit voltage. Can I make them bigger? Can I make the fill factor even bigger so that I can get higher efficiency? Those are the tasks that I have. Those are the scientific questions that I have to address. Here's one example just to make the point. Okay, a few years ago we were studying this system, poly-3-hexylthiophene P3HT with this soluble fullerene, and really lousy results. The fill factor was terrible, but we found, and others found, that if you annealed the sample, if you took it up to high temperature where the molecules could move around, you could make the fill factor a little better, and you could get a higher current. And if you went still farther, you could do still better, and this corresponds to about 5%. So there is an optimum length scale. The phase separation is spontaneous, but it's not always right. So one wants to be able to control the phase separation. And you see, I'm using this example just to make the point. You can change these things. In this case, and for good fundamental reasons, the open circuit voltage is much more fundamental. It's related to the electronic structure. The current is basically related to the morphology. If I have a very poor phase separation and I don't have good connectivity in those networks, then the current will be pretty low. So these are the kinds of things. This is what I would call fundamental parameter. This has to do with current has a lot to do with materials science and morphology. And the fill factor is dominated by recombination physics that I'll come back to. So here's a very old image that I've shown many times. This is a photo of a number of different semiconducting polymers with different molecular structures. They have different colors because they have different energy gaps. If you change the molecular structure, if you just go back a few slides to the ones I was showing you, if you change the molecular structure, you can change the energy gap. This is a large band gap polymer in solution. The energy gap of the polymer here is about 3 eV, so it does not absorb visible light. All the light comes through, so it's white, looks white. This is a polymer which has an energy gap of about 2.5 electron volts, so it allows green light to come through. This energy gap is smaller because only red light comes through, so one can do spectroscopy here by eye. 2 points. These are dilute solutions at relatively small volume fraction or weight fraction of polymer in a common solvent, organic solvent, or even water. But the important thing is that these are not just colored liquids. They can be viewed as inks, and these inks have electronic functionality. Okay? Gutenberg taught us about printing 1545. And today, scientists and engineers all over the world are using materials like this as inks and printing them. So the dream here is that we would be able to do that, to have a roll-to-roll process where I use a solution which has both the polymer and the fullerene in it, that I put that onto a plastic substrate, and that when I cast, and that I make solar cells of the kind that I showed you. So this is real, okay? This is happening. This is a roll-to-roll manufacturing plant for plastic solar cells at Konarka. This is in New Bedford, Massachusetts, a little bit south of Boston. This roll here is more than 5 feet wide. Okay? This is a plastic roll. We're depositing on that roll, and that's about this wide. Okay? That's the kind of image that I showed you earlier on the rooftop. It's about this wide. So what one is able to do here is to do roll-to-roll printing or coating with more than 5 feet at about 30 feet per minute. And if you think about that, at 7%, that would give you, in a year, enough solar cells to produce a gigawatt of power. That's like a nuclear power plant. So that's why we're excited with the potential. Fundamentals are done, but the efficiency is still not high enough. One second. Efficiency is still not high enough. I need to learn how to control the open circuit voltage. I need to learn how to control the short circuit current. I need to control the fill factor so that I can get to 7 or 10%. But if we can do that, then we'll have a revolution. Yes? You have to talk loud. I'm an old guy.
You spoke before that take it by phase separation.
Yes.
Now, if you do inkjet printing like you're doing, if you do printing like you do here,
Yes?
then what dictate that is the solvent evaporation.
Yes.
Now, this is something that you cannot really control because you have also hydrodynamics that drove everything, and you have the solvent to get out of the...
So this is a plant. I'm not going to answer your question. It works. But it's a plant that was built by Polaroid company to make multi-layer films for photography, right? And Polaroid went into bankruptcy, and so Konarka was able to buy a $250 million plant for $5 million. It's almost ideal. What goes on here is there are big vats that you can control the temperature of the solvent. There's a heater which controls the temperature on the roll. Okay. Behind this is 100 feet with 4 separate drying zones with different temperatures that you can control. So you begin to see what you can do. In fact, they have a lot of knobs, right? In the laboratory that, in our lab or in a university lab, we don't even have that many knobs. So yes, there's complexity here, but that's what this plant, and I will tell you that what's coming out of this plant is not very efficient, 3%. But the yield is really high. The process works. I don't think I'm allowed to tell you what the yield is, but it's really high. Usually that takes 10 years to get a process up to very high yield. This is working now, and it's working at high speed, and they're selling some product, but if we had 10%, it would be a big deal. So we got to get to 10%. What's the name of that company? Konarka, actually, the name is the name of a Indian sun god. There's a temple in India with that name, and there's another whole story that I can tell you about that over a drink later. All right, let's talk about the charge transfer process again and the origin of the open circuit voltage. Okay. So what did I say? What I said was you come in with a photon and you promote an electron from here to here, and then you get electron transfer. Think about that for a second. Under bright light, say one sun, you end up with a lot of holes here, and therefore you pin the Fermi level in the polymer here. And you end up with a lot of electrons here, so you pin the Fermi level in the fullerene here. Okay? Therefore, the open circuit voltage is the difference between those two quasi-Fermi levels. So the open circuit voltage is this number. The energy difference between the LUMO of the lowest unoccupied molecular energy orbital of the acceptor minus the top of the pi band, the highest occupied state of the polymer. Now, the system that I showed you earlier and the system that was being made on that plant right now is using poly-3-hexylthiophene, this polymer, and it turns out that the energetics are such that you get very fast electron transfer, but if you, and this is, I drew this more or less to scale, you absorb, let's say, a 2 eV photon, roughly 2 eV, and then you give more than half of it away in the charge transfer process, and you end up with an open circuit voltage which is only 0.6 volts. Now we don't want to waste all that energy. What we want to do is to either bring this electronic structure down, pull it down, or use a different acceptor that would bring this electronic structure up. For example, suppose I can make a new polymer which is more electronegative, okay? So that I just took this electronic structure and on my computer it's easy to do. I just brought it down. And now you see this energy is closer, the band offset is smaller. So the open circuit voltage would be correspondingly larger. And this is true. For example, with this polymer, which I told you a moment ago, we were able to get 6.5%. We actually get an open circuit voltage of 0.9 because we have pulled this thing down, and that's all been verified by XPS and et cetera. So you see, new materials. Fortunately, our colleagues, synthetic chemists, can synthesize new polymers. They are doing so. By bringing the electronic structure down, I can make the open circuit voltage larger. The goal would be to have the energy gap here approximately maybe a little bit bigger than silicon, because then I absorb most of the photons in the solar spectrum, and have just enough band offset to assure charge transfer. That's been a controversial area. Many people have expressed some doubt that one can have both of those. That is, to have a small gap and still get electron transfer. We recently have been working with one of my colleagues with a system where the band offset is only 0.1 eV, and we get charge transfer. So I think this is possible, but the important point here is for you to understand that the open circuit voltage comes about from this energy difference, and that we can hope to control that open circuit voltage by creating new polymers with well-defined electronic structure. I also, of course, want to get the energy gap right. So let's see. How does this open circuit voltage actually created? Well, let's just look at it. Okay. This is a simulated image. This is a donor region. This is an acceptor region. You get photoinduced electron transfer. At open circuit, you want to prevent the electrons from coming back. At open circuit, what you do is you make basically a little parallel plate capacitor across that interface. A parallel plate capacitor is a lovely device because the voltage drop across it compensates for the different Fermi levels in the two systems. And at open circuit, this is in dynamic electrochemical equilibrium. So you got to build up this charge across the interface. The interface is a few nanometers wide at most, not quite molecularly sharp, of course, but nearly so. Nothing like the width in a doped PN junction. If the interface were actually sharp, if it were literally atomically smooth, then the width of that junction would be limited by the, basically by the uncertainty principle. You have to have some spread. We talked about this. There's one other issue that I want to tell you about. So in this image, which this is think of this as a simulated image for a minute. Here's a heterojunction right here. Here's a nanoscale solar cell. There's a good continuous path all the way through it. Open circuit voltage occurs across this interface. But the amazing thing is that when we measure the open circuit voltage at the external contacts, we get the value that is predicted by the electronic structure on the previous slide. Okay? And you wake up in the middle of the night and you say to yourself, how is that possible? And the answer is there's only one way that's possible, and that is that all of the 100 billion solar cells per square centimeter in that image must be hooked up in parallel. Okay? And then you have to ask yourself, how could that be? I'm not that good. It has to happen by itself. And the answer is that you need to have charge selective transport layers. So you need a layer up here which transports electrons but doesn't transport holes, and then you would short together all of the black things without shorting the white ones. And similarly, you need a whole transport layer here which is electron blocking, and then you can make them all in parallel. That's the kind of thing we're trying to do. I'll give you one example in a few minutes. It's an important issue. So we're talking about self-assembly on several levels here. Now what happens? What happens is that first you absorb photons and you create this excited state, and you get charge transfer, and you create mobile carriers. You also, very shortly, there are traps at the interface, and you fill those traps, or you start to fill those traps. These mobile carriers are swept out of the film by the internal field that comes from the symmetry breaking. That sweep out time is just the thickness over the speed, the drift velocity, and the drift velocity is the electric field times the mobility, and the electric field is the voltage over the thickness, and you get this simple expression for the sweep out time. And that sweep out time is about a microsecond. I'll show you that in a minute. So I create these mobile carriers in much less than a picosecond. Think about the image I showed you before. And then I sweep them out from the internal built-in electric field, most of them, I hope. Some of them recombine through traps, etc. And the efficiency is determined by how many I get out. Now, it's very important, of course, that this sweep-out time be less than the recombination time, otherwise I won't get them out. So here's an expression for the current as a function of time at a given voltage. And what do I mean by that voltage? I'm talking about the internal voltage. Okay? There's a built-in potential. I'm applying a voltage on the outside, and the internal voltage is the difference. So at short circuit, the internal voltage is biggest. It's very important to understand this. At short circuit, the internal voltage is biggest, and the carriers are swept out very fast. Okay? As you change the external voltage to compensate the internal voltage, sweep out takes longer. At open circuit, nothing is swept out because the internal voltage is zero. And at open circuit, the only thing that can happen is recombination. And there you see it. At open circuit, you have a semi-log decay, an exponential decay, with a time constant that is, I've forgotten what it is, but it's whatever, some microseconds. So the important thing is that you want the transit time to be much faster than the recombination time so that you can get the carriers out. This says all of that, and these data, which were obtained by my colleague Robert Street at the Palo Alto Research Center show this, precisely this kind of evolution from sweep out to recombination. This is a different polymer at a different temperature, but the same kind of phenomena. Because it's at lower temperatures, the entire time scale is pushed out, but this is what is happening, a competition between sweep out by the internal field and recombination. Fortunately, one can create systems where the sweep out is fast enough that you can get the carriers out. Too much detail. So I have to, what do I have to do? I have to make the energy gap smaller so that as I said, the ideal energy gap would be almost like that of silicon, because then I would absorb most of the solar spectrum. I really have to make this right, the nanoscale heterostructure, and it's very important, for example, that I have good connectivity without any dead ends, so that I'm able to collect the charge. So let's look at this a bit. So here's the same image that I showed you before. You look at this and you sort of immediately see a quasi-periodic structure. In any direction, the length scale between light and dark looks to be about the same. So if one does a Fourier transform of that, you see a peak here. Peak is at the characteristic, is at the 1 over the characteristic length scale here. And the characteristic length scale here is about 20 nanometers. As I said earlier, looks like you can see connectivity. So that's the right length scale, because that means that if a photon is absorbed at the center of, say, the polymer domain, then the excitation can get to the interface before recombination, and you can get charge separation, and then you got the hole on one side and the electron on the other side, and you can sweep them out and you can go forward. Okay, I should say a little word about phase contrast TEM. I commented on it before. We're talking about using an electron beam, and the process is that, as I said before, the velocity of the electron beam is slower when you have a higher density of nuclei. Not so easy to get contrast between carbon fullerenes and carbon polymers, but since there are more carbon per unit volume in the fullerene, we actually can get some contrast by using phase contrast TEM. The way you look at it is schematically like this. You don't focus the electron beam on the surface because there's very little contrast. You defocus the beam and focus it well below, about 25 microns below the plane of the surface, and then you can get some contrast. This comes with some limitations. Those limitations are described by this contrast transfer function, which is a function of the length scale that you want to see and the defocus distance. So if you defocus by about 25 microns, it turns out that one is quite sensitive to length scales on the 10 to 20 nanometer regime. Yes?
What is the thickness of the layer that you feature in the TEM, and how does the thickness might change your order within it?
You're asking me, say it again.
I asked what is the thickness that you observe at the TEM.
The thickness of the film is about less than, roughly 100 nanometers,
Okay, and does
1,000 angstroms.
the thickness of the layer could change the
one is sensitive to the thickness of the film. If you have variations in the thickness of the film, then they will also give you an apparent contrast. It's thicker there, right? So that's something we worry about. And we do some AFM scans to try to check to see whether that thickness is coming into the problem. But that's right.
What I'm just aiming to ask is whether the way you prepare the sample for PEM
Yes,
or
is relevant.
it's a fact on the things to see that is not correlated to the actual solar cell which you prepare.
Right. No, you're exactly right. It's a very relevant question, and let me show you. Let me give you one example that will give you some sense of that. Okay. And okay, so this is the method, and we want to make sure that this contrast transfer function doesn't distort the image. That requires changing, for example, the defocus distance, and I'm not going to go into that in detail. What I'd like to do is no. I mean, obviously, it would, you know. But if you go to very large defocus distances, you start seeing the contrast transfer function coming in as, well, I will call it an artifact. It's not an artifact, it's just a distortion. Okay? So there is an optimum, and it turns out we use about 25 microns for the defocus. High spatial frequencies you're never going to see because at those length scales, the contrast transfer function is not sensitive. And, you know, there's a lot of other reasons why we have confidence. Just by annealing the sample, one sees these changes, as I said before. Now, let me move to cross-sectional images for just a second and come back to this question that was asked. I've been showing you top-down images. They're interesting, they're important, but I would really like to see cross-sectional images to see if I can actually collect the charge at these interfaces. Okay? As I said, the periodicity seems to be about right. So we've been doing that, and the way we do that, the way Ji-Sun Moon does that, she uses a focused ion beam to cut a thin slice of salami. Cut a thin slice through the sample. Okay? Take that thin slice out and do transmission electron microscopy through that thin slice. And if you're very good, and she is very good, you can make a thin slice that's 100 nanometers thick, and then you can trim it down to 60 nanometers thick, and you can use the focused ion beam to do that. I'm showing you those images here. This is a focused image. These are defocused images. The cutting by the field ion is very smooth and has been checked by AFM. So I think that's okay. And we get the same answer whether you get on this one film, on this one slice where you cut it to 120 nanometers and then you trim it over here down to 60 nanometers. These are the cross-sectional images. These are the kinds of things I've been showing you before. To get from here to here, this is the real data. Okay? To get from here to here, we have simply put a threshold on and enhanced the contrast. It's done honestly. We know how much fullerene is in there, 1:1. So we set the contrast threshold so that there's equal amount of black and white. But this is only for you and me to see and for me to show you. You can see every feature that is here, you can see it in here. Let's look at this one, for example. It's very clearly this one right here. So this is to guide your eye. These are the real data. Now let's take, for example, a line along here, and we have a digital information, and we'll just use it. So we can do, for example, a Fourier transform, get the same answer that we got with the top-down image, and we get the same answer for the 120 nanometers as for the 60 nanometer. You can also obviously calculate an autocorrelation function. So you take the intensity, that is the brightness at some point, and you multiply the brightness by brightness at a different point, and then you integrate that separation, and you get the autocorrelation function. An autocorrelation function has to start out at 1, and if it's quasi-periodic, you should see a peak here and maybe a second peak, and that periodicity should be the same. You see all of that here. So the length scale is 20-25 nanometers. And this is a very nice system, this poly-3-hexylthiophene, because we can see all this. I'll show you some more complicated system in a minute. All right.
Sorry?
Yes?
Can you estimate how much of each network is really connected from top to bottom?
I don't know the answer to that, but it's highly connected because I'm going to show you an example in a minute, I get there, where we get 100% quantum efficiency. Every photon that's absorbed leads us to an electron-hole pair, and we collect them all.
Yeah, but
So they're pretty well connected.
External quantum efficiency, or
External.
why wouldn't there be islands of PCBM and P3HT that are
Well,
not-
the answer to that is a complex question. Is it better? You're going to get phase separation. Is it better to have all the material in one big bunch over here and the other, or is if the interface energy is lower, then you want to have a lot of interface. Evidently, that's the case here, because we get a lot of interface. So, in a good system, you get good connectivity. Can we always do that? No. We were lucky here, and we continue to be somewhat lucky, but we have to learn how to control it. So, which gives me to the next point: controlling the morphology. One way to control the morphology, or begin to control the morphology, is to use a second solvent, okay? And what I'm showing you here is an example where we put in about 2% of a separate solvent. The second solvent is a very good solvent for the fullerene and has a much higher boiling point, so it's the last thing to leave. Keeps the fullerene in solution a little bit longer. And it turns out that that gives you better, sharper, more well-defined spectra for the polymer and increases the efficiency by nearly a factor of 2. So we're controlling the morphology, or I shouldn't use the word, we're affecting the morphology in a positive way. Saying we're controlling it is not right, but you get significant increases in the current and in the fill factor by using these processing additives. Want to look at that in detail, you can. In this case, with a smaller band gap polymer that goes out to significantly farther than the alkyl thiophene, you really need this help. So this is not a solved problem, but at least we're showing routes toward that solution. The additive is a good solvent for the fullerene, poor solvent for the polymer, helps you control the morphology. Let me go back to, because it's relevant to your question. So here, let's just find a good place. Let's take this one, for example. It looks like that's a dead end, right? That's the kind of thing that you were asking about. Looks like that's a dead end. But remember, this is only one very thin slice through the polymer. What about the next slice? Well, I presume, I infer that the next slice, this will go a little farther down, and eventually it comes to the electrode. I don't know that. I'm just guessing that. But you can find out. The way you would find out, and we're trying to do that, is by doing tomography, reconstructing a three-dimensional image and cutting it, digitally. How do you do that? Actually, to do that, you take a film and you first tilt it this way, and then you tilt it this way, and then you've got the information to reconstruct the three-dimensional image, and then you can do tomography. Okay? So people are starting to do this. I hope one day to be able to show you a movie, a set of images that will show that this point, or a point like this, does come to the electron. I don't have that data. I'm inferring that. Because, as I said, one infers high connectivity from the actual results.
Regarding the previous slide, that when you showed the EM slide, before going to tomography, today it is known that having EM, the use of other modes that can get you to see phase imaging, not contrast, but with the phase image of the electrons passing through the channel.
We should talk about this afterward.
Okay.
I'm not sure I understand, and I don't pretend to be a real expert on this, but we can talk about it afterwards. Yes?
I have another question. If you would use the carbon nanotube instead of buckyballs, would it yield?
People have tried that. See,
Wouldn't it yield a better
No.
electron conductor?
It'd be better electron conductor, but there are two problems with the carbon nanotubes. One of which is that half of them are metallic, and metallic would be shorts. So you have, first of all, have to separate out the semiconductor from the metal. Okay, that's being done. People are learning how to do that. The other problem is that the semiconducting nanotubes have quite a small gap, right? So that means you're going to lose all that energy in the charge. So people have tried this. It doesn't seem to be the right way to go. Maybe by using, and there have been some, for example, cadmium selenide was being studied, nanotubes. The idea there was what you're saying. But it's still open. I mean, that's one of the things that one might do, but carbon nanotubes won't work. All right, I want to show you one example. I'll show you one example of an interesting interlayer here. I'm going to put a layer of titanium oxide between the charge separating layer and the now why do I want to do that? There are a lot of reasons. One reason is that light is coming in and reflecting from an aluminum mirror and coming back out. Okay? And when you have that, you know from your elementary physics that at the surface of a metal, the electric field is zero. So the intensity might be 100 milliwatts per square centimeter coming in, but it's zero there. And it takes approximately a quarter wavelength for this to build back up. So what we need to do is to put in a spacer that puts this maximum in the middle of the charge separating film. We call that an optical spacer. And for that, we use titanium oxide, this sol gel processed titanium oxide, because almost perfect matching of the conduction band edge with the fullerene LUMO with aluminum so that we get a very good electron transport, and we get a very big barrier to hole transport. In other words, it's a charge selective layer of the kind that I suggested before. So this is, again, a fairly big story. I'm not going to go through it all, but by doing that, by having the electron blocker and, by having the electron transport collector and the hole blocker and the optical spacer, we get significant improvement in the collection efficiency, just because there's more brightness in the film. Okay. Device architecture, then, is an important issue. We want to be able to optimize the device architecture so that we can get as many charges out as we can so that we don't lose them. I showed you this before, but now I want to make it real. I said to you I want to bring the electronic structure down, and this polymer does so. It was synthesized by Mario Leclerc and his colleagues in Canada. It's a very interesting polymer. Very high temperature stability. You can take it up to 400 degrees C when it's a high molecular weight material. Very stable. The reason it's stable, by the way, is because this pi band is so deep that oxygen doesn't oxidize it. So you get both an larger open circuit voltage, and you get stability. Where am I? How much time do I have? Okay. So I'm not going to be able to go into this in detail. There are a lot of interesting features here. This gives you certified 6% using this titanium oxide. The open circuit voltage, instead of being 0.6, is now 0.9. And is in good agreement with what you expect from having pulled the electronic structure down. We need to go still farther. We need to make similar systems which have a smaller gap and maintain that large open circuit voltage. The synthetic approach is to use this class of materials but change the acceptor unit inside between these two thiophene. It looks like a general synthetic approach. Remains to be seen if we can get the gap down to as far as we would like to, but this is the kind of thing that is going on. In this system, as I said, we get 6 to 6.5%, but what's really important is that we get 100% quantum efficiency, or very near that. I don't have enough time to go into this in detail, but here's the measured current, but the film is very thin, so about 30% of the light just gets reflected out. If you correct for that, the external quantum efficiency is 90% or greater. So we're really collecting all the charge. Nearly every photon yields an electron hole pair, which I'm not surprised at because the charge transfer rate is so fast. But we're getting most of them out, and therefore the connectivity is quite good. By working hard, you can improve that a little bit. This is up and around 6.5%. This polymer could give us better results. If you look at the cross-sectional image, you don't see that column-like structure. It looks very horizontally striated, and you see that from the autocorrelation function. So there's hope here that if we can improve the morphology, I don't know how, working on that we could get this up above 8%. But as I said, recently with other polymers, recently reported people have demonstrated in excess of 8% with systems like this. If you take this PCD-TBT with the acceptor here, I'm telling you that the internal quantum efficiency is close to 100%. So if you use a laser here, in the middle of the absorption band, you expect to get high conversion efficiency. And you do. You get 17%. So the problem, of course, is that the energy gap is too large. We're missing all of the solar spectrum in the infrared. If we could do the same good job of photogeneration and charge collection with a smaller band gap polymer, we could get above 10%, 10, 15% with this kind of a concept. That's what we're trying to do. What limits the fill factor? We now understand that in terms of recombination of mobile carriers. I mentioned that. There's a lot more to say about it, but I'm not going to have time to talk about it here. By looking at the intensity dependence of the IV curves, one concludes that they all collapse if you divide out the intensity, meaning that this is a monomolecular decay. That, by the way, is consistent with those time dependence measurements I showed you earlier. Many things here. Let's go on. Interesting. First, let me show you this one. So this is, oops, the red dots here are amorphous silicon, which of course is a commercial product. The black dots here are, I got it wrong. The black dots are amorphous silicon. The red dots are this PCD TBT. They're about the same as amorphous silicon. Of course, amorphous silicon is a big time product. This has not been transferred onto this manufacturing line. If you go to very low light intensities, say room light, then these polymer solar cells become much better than amorphous silicon. It drops a lot because of, well, there's a whole story there, but as you see, in, for example, in room light under fluorescent lighting, these polymer solar cells are significantly more efficient than amorphous silicon. And there are some very interesting application possibilities in that regime. Okay. What can you hope to expect? So here's a plot of the kind of thing you could hope to expect. If you had high fill factor, and we have demonstrated in some systems a fill factor of 0.7, if you have a high external quantum efficiency, and there are some systems where we have demonstrated that, then depending on details, you can get, maybe 30%. But even if you put in all the losses that we're potentially aware of, this maximum is in excess of 15% with an energy gap of about 1.3 eV. We're here. Other people actually are a little higher, as I said, about 8%. So the technology pathway is there. We understand some of the science, but there are a lot of unsolved problems. The 8% was just reported in Advanced Materials in January. And I guess the question is, can we get to that kind of a theoretical limit? And the answer is that we have a lot of things that we can do. We can improve the absorption matching the solar spectrum. We can improve the collection efficiency. We can increase the open circuit. We can do all these things. And we've demonstrated all of those things, each of those things. The difficulty is to do them all in the same system. When we can do them all in the same system, then we can hope to get even tandem cells and, wow, too much. We can get to efficiencies of that high. So this is an interesting image. This is my rooftop in Santa Barbara. Okay? And I have silicon solar cells on because I can't get plastic ones yet. But it's great. Every morning when I get up, I go out and I look at the electric meter. It's running backwards. I'm selling electricity onto the grid. At the end of the month, I get my electric bill and it says 0. I pay about $1, maybe $2, because all during the day, or many days, I'm selling to the grid, and I buy power back at night, but the net is very close to 0. So what we'd like to do, of course, is this is expensive. This cost me a lot of money. Okay, let me put it in a context. It'll take, I'm guessing from cost of electricity, require about 12 years for the savings to pay back the capital investment. This is much too long. Cost of silicon solar cells is too high. And that cost has been coming down since 1954, when they were first discovered. There's very little more that one can take out of it. This technology, if we can do the things that I've talked about, manufacturing costs are very low. Okay? We get a lot of material in a roll-to-roll process with very little capital equipment expense. The materials costs are very small. These are expensive polymers, but they're only 100 nanometers thick. So if we can get to, or I shouldn't say if, because we will, when we can get to 12 to 15%, the cost will be way down below, will be significantly below $1 per watt, and then the payback time would be not 12 years, but maybe 3 years, whatever, depends on how optimistic one feels. Then it would really make a big difference, and one could begin to think about implementing it on the rooftop. Next question, obviously, is what about the lifetime? And the answer is the lifetime has to be long, or you wouldn't have a successful technology. We've demonstrated a year on the rooftop without any change in efficiency. You need barrier films. We have good barrier films. I'm pretty confident that we can get 10 years. We'll see. But that kind of work is going on, testing the lifetime, and the very first slide that I showed you was showing you that. Okay, I've talked about a lot of things. I'm going to give a lot of credit to my colleagues at Konarka who have done this kind of roll-to-roll manufacturing. I like to carry a sample around with me, but it gets to be more and more difficult at airports, so I didn't bring one today. These are the people who have contributed to this work. This is Sung-Hoon Park, who made all those solar cells with that high-efficiency polymer. This is Ji-Sun Moon, who cut the films. Ji-Sun Chinook Cho, who did all the work on field effect transistors, which I didn't have a chance to talk about. Titanium oxide work was brought into our group by Kwang Hee Lee, my colleague, and many other people. Sarah did all these beautiful work on intensity dependence, et cetera, and this is where we are, right there. Time to have a break. So we're late. Are there any other questions? I'm happy to answer. Yes.
Do you have the ability to check the charge separation and the charge collection efficiency separately in some kind of measurement, or it's still?
So do I have what?
Do we have in the beginning? In the beginning, you talk about Threestep.
Right.
Checking the absorption of the material, it's easy,
Yeah.
but the charge separation and charge collection.
Right. So
Is it possible to measure them
well,
separately?
we can certainly measure the charge collection. That's what that's what a solar cell does. And as I said, we have one example, at least, where the internal quantum efficiency is we're collecting essentially all the charge. Now, the charge separation efficiency we infer from the very fast charge transfer time, very high transfer rate, compared to any other process. There is no competing process, so we infer that probability of charge separation approaches unity. And I think that's solid. So, yeah, we can measure both separately.
Any question?
Can you somehow control the open circuit voltage by doping or somehow introducing carriers into your device?
I don't think that's a fruitful way to go. Think about the picture I showed, right? Where you have charge separation. You have charge separation because of the band offset in the heterojunction. Now, if I were to, for example, dope this material, I'd be putting donor levels below the band edge. That would decrease a little bit the open circuit voltage. I think the best way to control the open circuit voltage is to manipulate the electronic structure. Now, that of course is something that is unique to the organic chemistry. We make these materials, and in principle, we can fine-tune that, electronic structure. Now, I can't do that. Synthetic chemists have to do that, and of course, there's a limit to the fine-tuning that they can do. But they're doing okay. I think that's a better way than trying to dope.
Okay, one last question.
What about the exciton binding energy? Isn't that a limiting factor to the open circuit voltage?
It's a limiting factor to, I would put it another way. It's a limiting factor to getting charge separation, right? The argument would be that you have a minimum offset that you must have in order to overcome the exciton binding energy. Okay, so I have two comments to make. One is a sort of theoretical comment. Theoretical comment is when the energy gap gets small, the dielectric constant gets big, and the binding energy gets small. I think that's basic physics, and I think it's true. Okay. The other comment is that we're just finishing a paper with a new acceptor that was made by my colleague Fred Woodall, where the band offset is 0.1 eV, and we get charge transfer. So, of course, you're right, but you can get things right. I mean, the issue of exciton binding is important. We've always been on the side of the spectrum which suggests that the exciton binding energy is small, and we have good evidence for that in small band gap systems. But that's very much part of the discussion, controversy, whatever, within the field. But we have an example. 0.1 EV band offset, you get charge transfer.
Well, I'm afraid I'll have to cut this short because we already...
It wasn't short. It was...
That was wonderful. Thank you very much again.